Welcome to solverfy.
In this problem, we're asked to find the mass excesses of various isotopes, both in terms of atomic units as well as, atomic mass units, as well as mega electron volts per square of speed of light. I've done that for part A, which we're looking for helium, the mass excess for helium. So to do that, you take the mass in atomic mass units minus the atomic mass number, which is an integer, but I'm calling it a decimal, and we're going to assume, since we're subtracting from a number with units, that this number, the atomic mass number, as well has units. And we come up with a difference of 0.002603 atomic mass units for helium. We simply multiply that mass excess by our conversion factor here, going from atomic mass units to mega electron volts per square of speed of light. Doing that multiplication, we end up with 2.45 times, or 2.45 mega electron volts per square of speed of light. That was a case for helium, a very light element. Continue on to carbon. Notice that carbon atomic mass units is exactly 12. It's the reference point for the table. And I'm going to subtract again using the same process by the atomic mass number of carbon-12, which is 12. We end up with 0.000 atomic mass units. Again, it's the reference point for atomic mass units. We multiply by our mass excess in atomic mass units by our conversion factor. We end up, again, with 0.000 mega electron volts per square of speed of light for carbon-12. Next, we're looking for the mass excess for, I believe it's called strontium. Look it up here. Yeah, strontium. That was close. And same procedure. 85.909261 is its mass in atomic mass units. We're subtracting by 86 decimal, and we're assuming that it also has atomic mass units. We end up with a difference of negative 0.090739 atomic mass units. We multiply by our conversion factor this mass excess difference, and we get a mass excess of negative 84.52 mega electron volts per square of speed of light. This is a comparatively heavier element than the previous two, helium and carbon-12. For part D, we're asked to find the mass excess of a rather heavy element, which I didn't write down. I believe it's uranium-235. And its mass excess is again back in the positive. It's 0.043930 atomic mass units. We multiply the mass excess in atomic units by our conversion factor of 931.5 mega electron volts per atomic mass unit, and we end up with 40.92 mega electron volts over the speed of light squared. So looking at these, we went to light and moderate, which both had light and moderate mass elements, which both had positive mass excess values. We went to a mid-range one, strontium, which had a negative mass excess. We went to a heavy element, uranium-235, and had another positive mass excess. So examining the Appendix B more closely, the appendix of isotopes, you can see that our mass excesses are going to be 0 or positive from neutrons to oxygen 15. The mass excess is going to be negative for oxygen 16 to polonium 214. And it's going to be positive again. What is that element? From astatine 218 to onward, 294. These elements that can only exist in the laboratory. We can write an equation, or not an equation, a function for the mass excess sign in terms of both atomic number and atomic mass number A. And these can be the boundaries for each limit specification are taken from the atomic number in these from above and entered into the respective boundaries for our function of atomic number. The same can be done for the function of atomic mass number, from which boundary values are taken from the superscripts of above. And that is the solution to our problem.